Section 1 of Gray's Anatomy, Part 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Laurie Ann Walden. Anatomy of the Human Body, Part 3, by Henry Gray. Section 1. Angiology, Introduction. The vascular system is divided for descriptive purposes into a. The blood vascular system, which comprises the heart and blood vessels for the circulation of the blood, and b. The lymph vascular system, consisting of lymph glands and lymphatic vessels, through which a colorless fluid, the lymph, circulates. It must be noted, however, that the two systems communicate with each other and are intimately associated developmentally. The heart is the central organ of the blood vascular system and consists of a hollow muscle. By its contraction the blood is pumped to all parts of the body through a complicated series of tubes termed arteries. The arteries undergo enormous ramification in their course throughout the body, and end in minute vessels called arterioles, which in their turn open into a close-meshed network of microscopic vessels termed capillaries. After the blood has passed through the capillaries, it is collected into a series of larger vessels called veins, by which it is returned to the heart. The passage of the blood through the heart and blood vessels constitutes what is termed the circulation of the blood, of which the following is an outline. The human heart is divided by septa into right and left halves, and each half is further divided into two cavities, an upper termed the atrium, and a lower, the ventricle. The heart therefore consists of four chambers: two, the right atrium and right ventricle, forming the right half, and two, the left atrium and left ventricle, the left half. The right half of the heart contains venous or impure blood, the left, arterial or pure blood. The atria are receiving chambers, and the ventricles distributing ones. From the cavity of the left ventricle the pure blood is carried into a large artery, the aorta, through the numerous branches of which it is distributed to all parts of the body, with the exception of the lungs. In its passage through the capillaries of the body, the blood gives up to the tissues the materials necessary for their growth and nourishment, and at the same time receives from the tissues the waste products resulting from their metabolism. In so doing it is changed from arterial into venous blood, which is collected by the veins, and through them returned to the right atrium of the heart. From this cavity the impure blood passes into the right ventricle, and is thence conveyed through the pulmonary arteries to the lungs. In the capillaries of the lungs it again becomes arterialized, and is then carried to the left atrium by the pulmonary veins. From the left atrium it passes into the left ventricle, from which the cycle once more begins. The course of the blood from the left ventricle through the body, generally to the right side of the heart, constitutes the greater or systemic circulation, while its passage from the right ventricle through the lungs to the left side of the heart is termed the lesser or pulmonary circulation. It is necessary, however, to state that the blood which circulates through the spleen, pancreas, stomach, small intestine, and the greater part of the large intestine, is not returned directly from these organs to the heart, but is conveyed by the portal vein to the liver. In the liver this vein divides, like an artery, and ultimately ends in capillary-like vessels, or sinusoids, from which the rootlets of a series of veins, called the hepatic veins, arise. These carry the blood into the inferior vena cava, whence it is conveyed to the right atrium. From this it will be seen that the blood contained in the portal vein passes through two sets of vessels: 1. The capillaries in the spleen, pancreas, stomach, etc., and 2. The sinusoids in the liver. The blood in the portal vein carries certain of the products of digestion, the carbohydrates, which are mostly taken up by the liver cells and stored as glycogen, and the protein products, which remain in solution and are carried into the general circulation to the various tissues and organs of the body. Speaking generally, the arteries may be said to contain pure, and the veins impure blood. This is true of the systemic, but not of the pulmonary vessels, since it has been seen that the impure blood is conveyed from the heart to the lungs by the pulmonary arteries, and the pure blood returned from the lungs to the heart by the pulmonary veins. Arteries, therefore, must be defined as vessels which convey blood from the heart, and veins as vessels which return blood to the heart. Structure of arteries. The arteries are composed of three coats, an internal or endothelial coat, tunica intima of Kölliker, a middle or muscular coat, tunica media, and an external or connective tissue coat, tunica adventitia. The two inner coats together are very easily separated from the external, as by the ordinary operation of tying a ligature around an artery. If a fine string be tied forcibly upon an artery, and then taken off, the external coat will be found undivided, but the two inner coats are divided in the track of the ligature, and can easily be further dissected from the outer coat. The inner coat, tunica intima, can be separated from the middle by a little maceration, or it may be stripped off in small pieces. But on account of its friability, it cannot be separated as a complete membrane. It is a fine, transparent, colorless structure which is highly elastic, and, after death, is commonly corrugated into longitudinal wrinkles. The inner coat consists of 1. A layer of pavement endothelium, the cells of which are polygonal, oval, or fusiform, and have very distinct round or oval nuclei. This endothelium is brought into view most distinctly by staining with nitrate of silver. 2. A subendothelial layer, consisting of delicate connective tissue with branched cells lying in the interspaces of the tissue. In arteries of less than 2 mm in diameter, the subendothelial layer consists of a single stratum of stellate cells, and the connective tissue is only largely developed in vessels of a considerable size. 3. An elastic or fenestrated layer, which consists of a membrane containing a network of elastic fibers, having principally a longitudinal direction, and in which, under the microscope, small elongated apertures or perforations may be seen, giving it a fenestrated appearance. It was therefore called by Henle the fenestrated membrane. This membrane forms the chief thickness of the inner coat, and can be separated into several layers, some of which present the appearance of a network of longitudinal elastic fibers, and others a more membranous character, marked by pale lines having a longitudinal direction. In minute arteries the fenestrated membrane is a very thin layer, but in the larger arteries, and especially the aorta, it has a very considerable thickness. The middle coat, tunica media, is distinguished from the inner by its color and by the transverse arrangement of its fibers. In the smaller arteries it consists principally of plain muscle fibers in fine bundles, arranged in lamellae and disposed circularly around the vessel. These lamellae vary in number according to the size of the vessel, the smallest arteries having only a single layer, and those slightly larger 3 or 4 layers. It is to this coat that the thickness of the wall of the artery is mainly due. In the larger arteries, as the iliac, femoral, and carotid, elastic fibers unite to form lamellae which alternate with the layers of muscular fibers. These lamellae are united to one another by elastic fibers which pass between the muscular bundles, and are connected with the fenestrated membrane of the inner coat. In the largest arteries, as the aorta and innominate, the amount of elastic tissue is very considerable. In these vessels a few bundles of white connective tissue have also been found in the middle coat. The muscle fiber cells are about 50 microns in length, and contain well-marked rod-shaped nuclei, which are often slightly curved. The external coat, tunica adventitia, consists mainly of fine and closely felted bundles of white connective tissue, but also contains elastic fibers in all but the smallest arteries. The elastic tissue is much more abundant next the tunica media, and it is sometimes described as forming here, between the adventitia and media, a special layer, the tunica elastica externa of Henle. This layer is most marked in arteries of medium size. In the largest vessels the external coat is relatively thin, but in small arteries it is of greater proportionate thickness. In the smaller arteries it consists of a single layer of white connective tissue and elastic fibers, while in the smallest arteries, just above the capillaries, the elastic fibers are wanting, and the connective tissue of which the coat is composed becomes more nearly homogeneous the nearer it approaches the capillaries, and is gradually reduced to a thin membranous envelope which finally disappears. Some arteries have extremely thin walls in proportion to their size. This is especially the case in those situated in the cavity of the cranium and vertebral canal, the difference depending on the thinness of the external and middle coats. The arteries, in their distribution throughout the body, are included in thin fibro-areolar investments, which form their sheaths. The vessel is loosely connected with its sheath by delicate areolar tissue, and the sheath usually encloses the accompanying veins, and sometimes a nerve. Some arteries, as those in the cranium, are not included in sheaths. All the larger arteries, like the other organs of the body, are supplied with blood vessels. These nutrient vessels, called the vasa vasorum, arise from a branch of the artery, or from a neighboring vessel at some considerable distance from the point at which they are distributed. They ramify in the loose areolar tissue connecting the artery with its sheath, and are distributed to the external coat, but do not, in man, penetrate the other coats. In some of the larger mammals a few vessels have been traced into the middle coat. Minute veins return the blood from these vessels. They empty themselves into the vein or veins accompanying the artery. Lymphatic vessels are also present in the outer coat. Arteries are also supplied with nerves, which are derived from the sympathetic, but may pass through the cerebrospinal nerves. They form intricate plexuses upon the surfaces of the larger trunks, and run along the smaller arteries as single filaments, or bundles of filaments, which twist around the vessel and unite with each other in a plexiform manner. The branches derived from these plexuses penetrate the external coat and are distributed principally to the muscular tissue of the middle coat, and thus regulate, by causing the contraction and relaxation of this tissue, the amount of blood sent to any part. The capillaries. The smaller arterial branches, excepting those of the cavernous structure of the sexual organs, of the splenic pulp, and of the placenta, terminate in networks of vessels which pervade nearly every tissue of the body. These vessels, from their minute size, are termed capillaries. They are interposed between the smallest branches of the arteries and the commencing veins, constituting a network, the branches of which maintain the same diameter throughout. The meshes of the network are more uniform in shape and size than those formed by the anastomoses of the small arteries and veins. The diameters of the capillaries vary in the different tissues of the body, the usual size being about 8 microns. The smallest are those of the brain and the mucous membrane of the intestines, and the largest those of the skin and the marrow of bone, where they are stated to be as large as 20 microns in diameter. The form of the capillary net varies in the different tissues, the meshes being generally rounded or elongated. The rounded form of mesh is most common, and prevails where there is a dense network, as in the lungs, in most glands and mucous membranes, and in the cutis. The meshes are not of an absolutely circular outline, but more or less angular, sometimes nearly quadrangular or polygonal, or more often irregular. Elongated meshes are observed in the muscles and nerves, the meshes resembling parallelograms in form, the long axis of the mesh running parallel with the long axis of the nerve or muscle. Sometimes the capillaries have a looped arrangement, a single vessel projecting from the common network, and returning after forming one or more loops, as in the papillae of the tongue and skin. The number of the capillaries and the size of the meshes determine the degree of vascularity of a part. The closest network and the smallest interspaces are found in the lungs and in the choroid coat of the eye. In these situations the interspaces are smaller than the capillary vessels themselves. In the intertubular plexus of the kidney, in the conjunctiva, and in the cutis, the interspaces are from 3 to 4 times as large as the capillaries which form them. and in the brain from 8 to 10 times as large as the capillaries in their long diameters, and from 4 to 6 times as large in their transverse diameters. In the adventitia of arteries the width of the meshes is 10 times that of the capillary vessels. As a general rule, the more active the function of the organ, the closer is its capillary net, and the larger its supply of blood. The meshes of the network are very narrow in all growing parts, in the glands, and in the mucous membranes, wider in bones and ligaments which are comparatively inactive. Blood vessels are nearly altogether absent in tendons, in which very little organic change occurs after their formation. In the liver the capillaries take a more or less radial course toward the intralobular vein, and their walls are incomplete, so that the blood comes into direct contact with the liver cells. These vessels in the liver are not true capillaries, but sinusoids. They are developed by the growth of columns of liver cells into the blood spaces of the embryonic organ. Structure. The wall of a capillary consists of a fine transparent endothelial layer composed of cells joined edge to edge by an interstitial cement substance and continuous with the endothelial cells which line the arteries and veins. When stained with nitrate of silver, the edges which bound the epithelial cells are brought into view. These cells are of large size and of an irregular polygonal or lanceolate shape, each containing an oval nucleus which may be displayed by carmine or hematoxylin. Between their edges, at various points of their meeting, roundish dark spots are sometimes seen which have been described as stomata, though they are closed by intercellular substance. They have been believed to be the situations through which the colorless corpuscles of the blood, when migrating from the blood vessels, emerge. But this view, though probable, is not universally accepted. Collisal describes these cells as having a rather more complex structure. He states that each consists of two parts, of hyaline ground plates, and of a protoplasmic granular part, in which is embedded the nucleus, on the outside of the ground plates. The hyaline internal coat of the capillaries does not form a complete membrane, but consists of plates which are inelastic, and though in contact with each other are not continuous. When, therefore, the capillaries are subjected to intravascular pressure, the plates become separated from each other. The protoplasmic portions of the cells, on the other hand, are united together. In some organs, for example the glomeruli of the kidneys, intercellular cement cannot be demonstrated in the capillary wall, and the cells are believed to form a syncytium. In many situations a delicate sheath or envelope of branched nucleated connective tissue cells is found around the simple capillary tube, particularly in the larger ones, and in other places, especially in the glands, the capillaries are invested with retiform connective tissue. Sinusoids. In certain organs, for example, the heart, the liver, the suprarenal and parathyroid glands, the glomus caroticum and glomus coccygeum, the smallest blood vessels present various differences from true capillaries. They are wider, with an irregular lumen, and have no connective tissue covering, their endothelial cells being in direct contact with the cells of the organ. Moreover, they are either arterial or venous, and not intermediate, as are the true capillaries. These vessels have been called sinusoids by Minot. They are formed by columns of cells or trabeculae pushing their way into a large blood vessel or blood space and carrying its endothelium before them. At the same time the wall of the vessel or space grows out between the cell columns. Structure of veins. The veins, like the arteries, are composed of three coats, internal, middle, and external. And these coats are, with the necessary modifications, analogous to the coats of the arteries, the internal being the endothelial, the middle the muscular, and the external the connective tissue or areolar. The main difference between the veins and the arteries is in the comparative weakness of the middle coat in the former. In the smallest veins the three coats are hardly to be distinguished. The endothelium is supported on a membrane separable into two layers, the outer of which is the thicker, and consists of a delicate nucleated membrane, adventitia, while the inner is composed of a network of longitudinal elastic fibers, media. In the veins next above these in size (0.4 millimeters in diameter), according to Kuliker, a connective tissue layer containing numerous muscle fibers circularly disposed can be traced, forming the middle coat, while the elastic and connective tissue elements of the outer coat become more distinctly perceptible. In the middle-sized veins the typical structure of these vessels becomes clear. The endothelium is of the same character as in the arteries, but its cells are more oval and less fusiform. It is supported by a connective tissue layer consisting of a delicate network of branched cells, and external to this is a layer of elastic fibers disposed in the form of a network in place of the definite fenestrated membrane seen in the arteries. This constitutes the internal coat. The middle coat is composed of a thick layer of connective tissue with elastic fibers intermixed in some veins with a transverse layer of muscular tissue. The white fibrous element is in considerable excess, and the elastic fibers are in much smaller proportion in the veins than in the arteries. The outer coat consists, as in the arteries, of areolar tissue, with longitudinal elastic fibers. In the largest veins the outer coat is from 2 to 5 times thicker than the middle coat, and contains a large number of longitudinal muscle fibers. These are most distinct in the inferior vena cava, especially at the termination of this vein in the heart, in the trunks of the hepatic veins, in all the large trunks of the portal vein, and in the external iliac, renal, and azygous veins. In the renal and portal veins they extend through the whole thickness of the outer coat, but in the other veins mentioned a layer of connective and elastic tissue is found external to the muscular fibers. All the large veins which open into the heart are covered for a short distance with a layer of striped muscular tissue continued onto them from the heart. Muscular tissue is wanting: 1. In the veins of the maternal part of the placenta; 2. In the venous sinuses of the dura mater and the veins of the pia mater of the brain and medulla spinalis; 3. In the veins of the retina; 4. In the veins of the cancellous tissue of bones; 5. In the venous spaces of the corpora cavernosa. The veins of the above-mentioned parts consist of an internal endothelial lining supported on one or more layers of areolar tissue. Most veins are provided with valves which serve to prevent the reflux of the blood. Each valve is formed by a reduplication of the inner coat, strengthened by connective tissue and elastic fibers, and is covered on both surfaces with endothelium, the arrangement of which differs on the two surfaces. On the surface of the valve next the wall of the vein the cells are arranged transversely, while on the other surface, over which the current of blood flows, the cells are arranged longitudinally in the direction of the current. Most commonly two such valves are found placed opposite one another, more especially in the smaller veins or in the larger trunks at the point where they are joined by smaller branches. Occasionally there are 3, and sometimes only 1. The valves are semilunar. They are attached by their convex edges to the wall of the vein. The concave margins are free, directed in the course of the venous current, and lie in close apposition with the wall of the vein as long as the current of blood takes its natural course. If, however, any regurgitation takes place, the valves become distended, their opposed edges are brought into contact, and the current is interrupted. The wall of the vein on the cardiac side of the point of attachment of each valve is expanded into a pouch or sinus, which gives to the vessel, when injected or distended with blood, a knotted appearance. The valves are very numerous in the veins of the extremities, especially of the lower extremities, these vessels having to conduct the blood against the force of gravity. They are absent in the very small veins, that is, those less than 2 millimeters in diameter, also in the vena cavae, hepatic, renal, uterine, and ovarian veins. A few valves are found in each spermatic vein, and one also at its point of junction with the renal vein or inferior vena cava, respectively. The cerebral and spinal veins, the veins of the cancellated tissue of bone, the pulmonary veins, and the umbilical vein and its branches are also destitute of valves. A few valves are occasionally found in the azygous and intercostal veins. Rudimentary valves are found in the tributaries of the portal venous system. The veins, like the arteries, are supplied with nutrient vessels, vasa vasorum. Nerves also are distributed to them in the same manner as to the arteries, but in much less abundance. End of section 1.
Section 2 of Gray's Anatomy, Part 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Anatomy of the Human Body, Part 3, by Henry Gray. The blood. The blood is an opaque, rather viscous fluid of a bright red or scarlet color when it flows from the arteries, of a dark red or purple color when it flows from the veins. It is salt to the taste and has a peculiar faint odor and an alkaline reaction. Its specific gravity is about 1.06, and its temperature is generally about 37 degrees, though varying slightly in different parts of the body. General composition of the blood. Blood consists of a fairly yellow fluid, the plasma or liquor sanguinis, in which are suspended numerous minute particles, the blood corpuscles, the majority of which are colored and give the blood its red tint. If a drop of blood be placed on a thin layer on a glass slide and examined under the microscope, a number of these corpuscles will be seen floating in the plasma. The blood corpuscles are of three kinds: 1. Colored corpuscles or erythrocytes, 2. Colorless corpuscles or leukocytes, and 3. Blood platelets. 1. Colored or red corpuscles, erythrocytes. When examined under the microscope, are seen to be circular discs, biconcave in profile. The disc has no nucleus, but in consequence of its biconcave shape, presents, according to the alterations of focus under an ordinary high power, a central part, sometimes bright, sometimes dark, which has the appearance of a nucleus. It is to the aggregation of the red corpuscles that the blood owes its red hue, although when examined by transmitted light, their color appears to be only a faintly reddish yellow. The corpuscles vary slightly in size even in the same drop of blood, but the average diameter is about 7.5 microns, and the thickness about 2 microns. Footnote: a micromillimeter, or micron, is 1/1000th of a millimeter, or 1/25,000th of an inch. End note. Besides these, there are found certain smaller corpuscles of about 1/2 of the size just indicated. These are termed microcytes, and are very scarce in normal blood. In diseased conditions, for example anemia, however, they are more numerous. The number of red corpuscles in the blood is enormous; between 4 million and 5 million are contained in a cubic millimeter. Power states that the red corpuscles of an adult would present an aggregate surface of about 3,000 square yards. If the web of a living frog's foot be spread out and examined under the microscope, the blood is seen to flow in a continuous stream through the vessels, and the corpuscles show no tendency to adhere to each other or to the wall of the vessel. Doubtless the same is the case in the human body, but when human blood is drawn and examined on a slide without reagents, the corpuscles tend to collect into heaps, like rouleaux of coins. It has been suggested that this phenomenon may be explained by alteration in surface tension. During life, the red corpuscles may be seen to change their shape under pressure so as to adapt themselves, to some extent, to the size of the vessel. They are, however, highly elastic, and speedily recover their shape when the pressure is removed. They are readily influenced by the medium in which they are placed. In water they swell up, lose their shape, and become globular, endosmosis. Subsequently, the hemoglobin is dissolved out, and the envelope can barely be distinguished as a faint circular outline. Solutions of salt or sugar, denser than the plasma, give them a stellate or crenated appearance, exosmosis. But the usual shape may be restored by diluting the solution to the same tonicity as the plasma. The crenated outline may be produced as the first effect of the passage of an electric shock. Subsequently, if sufficiently strong, the shock ruptures the envelope. A solution of salt, isotonic with the plasma, merely separates the blood corpuscles mechanically without changing their shape. Two views are held with regard to the structure of the erythrocytes. The older view, that of Rolette, supposes that the corpuscle consists of a sponge work or stroma permeated by a solution of hemoglobin. Schaefer, on the other hand, believes that the hemoglobin solution is contained within an envelope or membrane, and the facts stated above with regard to the osmotic behavior of the erythrocyte support this belief. The envelope consists mainly of lecithin, cholesterin, and nucleoprotein. The colorless corpuscles or leukocytes are of various sizes, some no larger, others smaller than the red corpuscles. In human blood, however, the majority are rather larger than the red corpuscles and measure about 10 microns in diameter. On the average, from 7,000 to 12,000 leukocytes are found in each cubic millimeter of blood. They consist of minute masses of nucleated protoplasm and exhibit several varieties, which are differentiated from each other chiefly by the occurrence or non-occurrence of granules in their protoplasm and by the staining reactions of these granules when present. The most numerous, 60%, and important are irregular in shape, possessed of the power of amoeboid movement, and are characterized by nuclei which often consist of 2 or 3 parts, multipartite, connected together by fine threads of chromatin. The protoplasm is clear and contains a number of very fine granules, which stain with acid dyes such as eosin or with neutral dyes, and are therefore called oxyphil or neutrophil. These cells are termed the polymorphonuclear leukocytes. 2. A second variety comprises from 1 to 4% of the leukocytes. They are larger than the previous kind and are made up of coarsely granular protoplasm, the granules being highly refractile and grouped around single nuclei of horseshoe shape. The granules stain deeply with eosin, and the cells are therefore often termed eosinophil corpuscles. 3. The third variety is called the hyaline cell or macrocyte. This is usually about the same size as the eosinophil cell, and when at rest is spherical in shape and contains a single round or oval nucleus. The protoplasm is free from granules, but it is not quite transparent, having the appearance of ground glass. 4. The fourth kind of colorless corpuscle is designated the lymphocyte, because it is identical with the cell derived from the lymph glands or other lymphoid tissue. It is the smallest of the leukocytes and consists chiefly of a spheroidal nucleus with a very little surrounding protoplasm of a homogeneous nature. It is regarded as the immature form of the hyaline cell. The third and fourth varieties together constitute from 20 to 30% of the colorless corpuscles, but of these 2 varieties the lymphocytes are by far the more numerous. Leukocytes having in their protoplasm granules which stain with basic dyes, basophil, have been described as occurring in human blood, but they are rarely found except in disease. The colorless corpuscles are very various in shape in living blood, because many of them have the power of constantly changing their form by protruding finger-shaped or filamentous processes of their substance, by which they move and take up granules from the surrounding medium. In locomotion, the corpuscle pushes out a process of its substance, a pseudopodium as it is called, and then shifts the rest of the body into it. In the same way, when any granule or particle comes in its way, the corpuscle wraps a pseudopodium around it, and then withdraws the pseudopodium with the contained particle into its own substance. By means of these amoeboid properties, the cells have the power of wandering or emigrating from the blood vessels by penetrating their walls, and thus finding their way into the extravascular spaces. A chemical investigation of the protoplasm of the leukocytes shows the presence of nucleoprotein and of globulin. The occurrence of small amounts of fat, lecithin, and glycogen may also be demonstrated. The blood platelets are discoid or irregularly shaped, colorless, refractile bodies, much smaller than the red corpuscles. Each contains a central chromatin mass resembling a nucleus. Blood platelets possess the power of amoeboid movement. When blood is shed, they rapidly disintegrate and form granular masses, setting free prothrombin and the substance called by Howell thromboplastin. It is doubtful whether they exist normally in circulating blood. End of section 2.
Of Gray's Anatomy, Part 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Julie Vermolligen. Anatomy of the Human Body, Part 3, by Henry Gray. Development of the Vascular System, Part 1. Blood vessels first make their appearance in several scattered vascular areas, which are developed simultaneously between the entoderm and the mesoderm of the yolk sac, i.e., outside the body of the embryo. Here a new type of cell, The angioblast, or vasoformative cell, is differentiated from the mesoderm. These cells, as they divide, form small, dense, syncytial masses, which soon join with similar masses by means of fine processes to form plexuses. These plexuses increase both by division and growth of its cells and by the addition of new angioblasts, which differentiate from the mesoderm. Within these solid plexuses, and also within the isolated masses of angioblasts, vacuoles appear through liquefaction of the central part of the syncytium into plasma. The lumen of the blood vessels thus formed is probably intracellular. The flattened cells at the periphery form the endothelium. The nucleated red blood corpuscles develop either from small masses of the original angioblast left attached to the inner wall of the lumen or directly from the flat endothelial cells. In either case, the syncytial mass thus formed projects from and is attached to the wall of the vessel. Such a mass is known as a blood island, and hemoglobin gradually accumulates within it. Later, the cells on the surface round up, giving the mass a mulberry-like appearance. Then the red blood cells break loose and are carried away in the plasma. Such free blood cells continue to divide. The term blood island was originally used for the syncytial masses of angioblasts found in the area vasculosa, but it is probably best to limit the term to the masses within the lumen from which the red blood cells arise, as Sabin has done. Blood islands have been seen in the area vasculosa, in the omphalocement vein and arteries, and in the dorsal aorta. The differentiation of angioblasts from the mesoderm occurs not only in the area vasculosa, but within the embryo, and probably most of the larger blood vessels are developed in situ in this manner. This process of the differentiation of angioblasts from the mesoderm probably ceases in different regions of the embryo at different periods, and after its cessation new vessels are formed by sprouts from vessel already laid down in the form of capillary plexuses. The first rudiment of the heart appears as a pair of tubular vessels which are developed in the splanchnople of the pericardial area. These are named the primitive aortae, and a direct continuity is soon established between them and the vessels of the yolk sac. Each receives anteriorly a vein, the vitelline vein, from the yolk sac, and is prolonged backward on the lateral aspect of the notochord under the name of the dorsal aorta. The dorsal aortae give branches to the yolk sac, and are continued backward through the body stalk, as the umbilical arteries to the villi of the chorion. Ethernet describes the circulation in an embryo, which he estimates to be about 13 days old. The rudiment of the heart is situated immediately below the foregut, and consists of a short stem. It gives off two vessels, the primitive aortae, which run backward, one on either side of the notochord, and then pass into the body stalk, along which they are carried to the chorion. From the chorionic villi the blood is returned by a pair of umbilical veins, which unite in the body stalk to form a single vessel and subsequently encircle the mouth of the yolk sac and open into the heart. At the junction of the yolk sac and body stalk, each vein is joined by a branch from the vascular plexus of the yolk sac. From his observations, it seems that in the human embryo the chorionic circulation is established before that on the yolk sac. By the forward growth and flexure of the head, the pericardial area and the anterior portions of the primitive aortae are folded backward on the ventral aspect of the foregut, and the original relation of the somatoplar and splanchnopolar layers of the pericardial area is reversed. Each primitive aorta now consists of a ventral and a dorsal part connected anteriorly by an arch. These three parts are named respectively the anterior ventral aorta, the dorsal aorta, and the first cephalic arch. The vitelline veins, which enter the embryo through the anterior wall of the umbilical orifice, are now continuous with the posterior ends of the anterior ventral aorta. With the formation of the tail fold, the posterior parts of the primitive aortae are carried forward in a ventral direction to form the posterior ventral aortae and primary caudal arches. In the pericardial region, the two primitive aortae grow together and fuse to form a single tubular heart, the posterior end of which receives the two vitelline veins, while from its anterior end the two anterior ventral aortae emerge. The first cephalic arches pass through the mandibular arches, and behind them 5 additional pairs subsequently develop, so that altogether 6 pairs of aortic arches are formed. The 5th arches are very transitory vessels connecting the ventral aortae with the dorsal ends of the 6th arches. By the rhythmical contraction of the tubular heart, the blood is forced through the aortae and blood vessels of the vascular area, from which it is returned to the heart by the vitelline veins. This constitutes the vitelline circulation, and by means of it nutriment is absorbed from the org vitalis. The vitelline veins at first open separately into the posterior end of the tubular heart, but after a time their terminal portions fuse to form a single vessel. The vitelline veins ultimately drain the blood from the digestive tube and are modified to form the portal vein. This is caused by the growth of the liver, which interrupts their direct continuity with the heart, and the blood returned by them circulates through the liver before reaching the heart. With the atrophy of the yolk sac, the vitelline circulation diminishes and ultimately ceases, while an increasing amount of blood is carried through the umbilical arteries to the villi of the chorion. Subsequently, as the non-placental chorionic villi atrophy, their vessels disappear, and then the umbilical arteries convey the whole of their contents to the placenta, whence it is returned to the heart by the umbilical veins. In this manner the placental circulation is established, and by means of it nutritive materials are absorbed from, and waste products given up to the maternal blood. The umbilical veins, like the vitelline, undergo interruption in the developing liver, and the blood returned by them passes through this organ before reaching the heart. Ultimately, the right umbilical vein shrivels up and disappears. During the occurrence of these changes, great alterations take place in the primitive heart and blood vessels. Further development of the heart. Between the endothelial lining and the outer wall of the heart, there exists for a time an intricate trabecular network of mesodermal tissue from which, at a later stage, the musculi papillaris, chordae tenonii, and trabeculae are developed. The simple tubular heart, already described, becomes elongated and bends on itself so as to form an S-shaped loop, the anterior part bending to the right and the posterior part to the left. The intermediate portion arches transversely from left to right, and then turns sharply forward into the anterior part of the loop. Slight contractions make their appearance in the tube, and divide it from behind forward into 5 parts, viz. 1. The sinus venosus, 2. The primitive atrium, 3. The primitive ventricle, 4. The bulbus cordis, and 5. The truncus arteriosus. The constriction between the atrium and ventricle constitutes the arterial canal and indicates the site of the future atrioventricular valves. The sinus venosus is at first situated in the septum transversum, a layer of mesoderm in which the liver and the central tendon of the diaphragm are developed, behind the primitive atrium, and is formed by the union of the vitelline veins. The veins or ducts of Cuvier from the body of the embryo and the umbilical veins from the placenta subsequently open into it. The sinus is at first transversely and opens by a median aperture into the primitive atrium. Soon, however, it assumes an oblique position and becomes crescentic in form. Its right half or horn increases more rapidly than the left, and the opening into the atrium now communicates with the right portion of the atrial cavity. The right horn and transverse portion of the sinus ultimately become incorporated with and form a part of the adult right atrium, the line of union between it and the auricula being indicated in the interior of the atrium by a vertical crest, the crista terminalis of His. The left horn, which ultimately receives only the left duct of Cuvier, persists as the coronary sinus. The vitelline and umbilical veins are soon replaced by a single vessel, the inferior vena cava, and the three veins, inferior vena cava and right and left Cuvierian ducts, open into the dorsal aspect of the atrium by a common slit-like aperture. The upper part of this aperture represents the opening of the permanent superior vena cava, the lower that of the inferior vena cava, and the intermediate part the orifice of the coronary sinus. The slit-like aperture lies obliquely and is guarded by two halves, the right and left venous valves. Above the opening these unite with each other and are continuous with the fold, named the septum spurium. Below the opening they fuse to form a triangular thickening, the spina vestibuli. The right venous valve is retained. A small septum, the sinus septum, grows from the posterior wall of the sinus venosus, diffused with the valve, and divided into two parts, an upper, the valve of the inferior vena cava, and a lower, the valve of the coronary sinus. The extreme upper portion of the right venous valve, together with the septum spurium, form the crista terminalis already mentioned. The upper and middle thirds of the left venous valve disappear. The lower third is continued into the spina vestibuli, and later fuses with the septum secundum of the atria, and takes part in the formation of the limbus fossae ovalis. The atrial canal is at first a short straight tube connecting the atrial with the ventricular portion of the heart, but its growth is relatively slow, and it becomes overlapped by the atria and ventricles, so that its position on the surface of the heart is indicated only by an annular constriction. Its lumen is reduced to a transverse slit, and two thickenings appear, one on its dorsal and another on its ventral wall, or endocardial cushions, as they are termed, project into the canal, and, meeting in the middle-line, unite to form the septum intermedium, which divides the canal into two channels, the future right and left atrioventricular orifices. The primitive atrium grows rapidly and partially encircles the bulbus cordis. The groove against which the bulbus cordis lies is the first indication of a division into right and left atria. The cavity of the primitive atrium becomes subdivided into right and left chambers by a septum, the septum primum, which grows downward into the cavity. For a time the atria communicate with each other by an opening, the ostium primum of Born, below the free margin of the septum. This opening is closed by the union of the septum primum with the septum intermedium, and the communication between the atria is re-established through an opening which is developed in the upper part of the septum primum. This opening is known as a foramen ovale, ostium secundum of Born, and persists until birth. A second septum, the septum secundum, semilunar in shape, grows downward from the upper wall of the atrium, immediately to the right of the primary septum and foramen ovale. Shortly after birth it fuses with the primary septum, and by this means the foramen ovale is closed. But sometimes the fusion is incomplete, and the upper part of the foramen remains patent. The limbus fossae ovalis denotes the free margin of the septum secundum. Issuing from each lung is a pair of pulmonary veins. Each pair unites to form a single vessel, and these in turn join in a common trunk which opens into the left atrium. Subsequently, the common trunk and the two vessels forming it expand and form the vestibule, or greater part of the atrium, the expansion reaching as far as the openings of the four vessels, so that in the adult all four veins open separately into the left atrium. The primitive ventricle becomes divided by a septum, the septum inferius or ventricular septum, which grows upward from the lower part of the ventricle, its position being indicated on the surface of the heart by a furrow. Its dorsal part increases more rapidly than its ventral portion, and fuses with the dorsal part of the septum intermedium. For a time an interventricular foramen exists above its ventral portion, but this foramen is ultimately closed by the fusion of the aortic septum with the ventricular septum. When the heart assumes its S-shaped form, the bulbus cordis lies ventral to and in front of the primitive ventricle. The adjacent walls of the bulbus cordis and ventricle approximate, fuse, and finally disappear, and the bulbus cordis now communicates freely with the right ventricle, while the junction of the bulbus with the truncus arteriosus is brought directly ventral to and applied to the atrial canal. By the upgrowth of the ventricular septum, the bulbus cordis is in great measure separated from the left ventricle, but remains an integral part of the right ventricle, of which it forms the infundibulum. The truncus arteriosus and bulbus cordis are divided by the aortic septum. This makes its appearance in three portions. 1. Two distal ridge-like thickenings project into the lumen of the tube. These increase in size and ultimately meet and fuse to form a septum, which takes a spiral course toward the proximal end of the truncus arteriosus. It divides the distal part of the truncus into two vessels, the aorta and pulmonary artery, which lie side by side above, but near the heart. The pulmonary artery is in front of the aorta. 2. 4 endocardial cushions appear in the proximal part of the truncus arteriosus in the region of the future semilunar valves. The manner in which these are related to the aortic septum is described below. 3. 2 endocardial thickenings, anterior and posterior, develop in the bulbus cordis and unite to form a short septum. This joins above with the aortic septum and below with the ventricular septum. The septum grows down into the ventricle as an oblique partition, which ultimately blends with the ventricular septum in such a way as to bring the bulbus cordis into communication with the pulmonary artery, and through the latter with the sixth pair of aortic arches, while the left ventricle is brought into continuity with the aorta, which communicates with the remaining aortic arches. End of section 3. Gray's Anatomy Part 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Julie van Mallegem. Anatomy of the Human Body, Part 3, by Henry Gray. Development of the Vascular System, Part 2. The valves of the heart. The atrioventricular valves are developed in relation to the atrial canal. By the upward expansion of the bases of the ventricles, the canal becomes invaginated into the ventricular cavities. The invaginated margin forms the rudiments of the lateral cusps of the atrioventricular valves. The medial or septal cusps of the valves are developed as downward prolongations of the septum intermedium. The aortic and pulmonary semilunar valves are formed from 4 endocardial thickenings, an anterior, a posterior, and 2 lateral, which appear at the proximal end of the truncus arteriosus. As the aortic septum grows downward, it divides each of the lateral thickenings into 2, thus giving rise to 6 thickenings, the rudiments of the semilunar valves, 3 at the aortic and 3 at pulmonary orifice. Further development of the arteries. Recent observations show that practically none of the main vessels of the adult arise as such in the embryo. In the side of each vessel a capillary network forms, and by the enlargement of definite paths in this the larger arteries and veins are developed. The branches of the main arteries are not always simple modifications of the vessels of the capillary network, but may arise as new outgrowths from the enlarged stem. It has been seen that each primitive aorta consists of a ventral and a dorsal part, which are continuous through the first aortic arch. The dorsal aortae at first run backward, separately on either side of the notochord, but about the 3rd week they fuse from about the level of the 4th thoracic to that of the 4th lumbar segment to form a single trunk, the descending aorta. The first aortic arches run through the mandibular arches, and behind them 5 additional pairs are developed within the visceral arches, so that, in all, 6 pairs of aortic arches are formed. The first and second arches pass between the ventral and dorsal aortae, while the others arise at first by a common trunk from the truncus arteriosus, but end separately in the dorsal aortae. As the neck elongates, the ventral aortae are drawn out, and the 3rd and 4th arches arise directly from these vessels. In fishes, these arches persist, and give off branches to the gills, in which the blood is oxygenated. In mammals some of them remain as permanent structures, while others disappear or become obliterated. The anterior ventral aortae. These persist on both sides. The right forms a. the innominate artery, b. the right common and external carotid arteries. The left gives rise to a. the short portion of the aortic arch, which reaches from the origin of the innominate artery to that of the left common carotid artery, b. the left common and external carotid arteries. The aortic arches. The first and second arches disappear early, but the dorsal end of the second gives origin to the stapedial artery, a vessel which atrophies in man but persists in some mammals. It passes through the ring of the stapes and divides into supraorbital, infraorbital, and mandibular branches, which follow the 3 divisions of the trigeminal nerve. The infraorbital and mandibular arise from a common stem, the terminal part of which anastomoses with the external carotid. On the obliteration of the stapedial artery, this anastomosis enlarges and forms the internal maxillary artery, and the branches of the stapedial artery are now branches of this vessel. The common stem of the infraorbital and mandibular branches passes between the 2 roots of the auriculotemporal nerve and becomes the middle meningeal artery. The original supraorbital branch of the stapedial is represented by the orbital twigs of the middle meningeal. The 3rd aortic arch constitutes the commencement of the internal carotid artery, and is, therefore, named the carotid arch. The 4th right arch forms the right subclavian as far as the origin of its internal mammary branch, while the 4th left arch constitutes the arch of the aorta between the origin of the left carotid artery and the termination of the ductus arteriosus. The 5th arch disappears on both sides. The 6th right arch disappears. The 6th left arch gives off the pulmonary arteries and forms the ductus arteriosus. This duct remains pervious during the whole of fetal life, but is obliterated a few days after birth. His showed that in the early embryo the right and left arches each gives a branch to the lungs, but that later both pulmonary arteries take origin from the left arch. The dorsal aortae persist and form the continuations of the internal carotid arteries. These arteries pass to the brain, and each divides into an anterior and a posterior branch, the former giving off the ophthalmic and the anterior and middle cerebral arteries, while the latter turns back and joins the cerebral part of the vertebral artery. Behind the third arch, the right dorsal aorta disappears as far as the point where the two dorsal aortae fuse to form the descending aorta. The part of the left dorsal aorta between the third and fourth arches disappears, while the remainder persists to form the descending part of the arch of the aorta. A constriction, the aortic isthmus, is sometimes seen in the aorta between the origin of the left subclavian and the attachment of the ductus arteriosus. Sometimes the right subclavian artery arises from the aortic arch distal to the origin of the left subclavian and passes upward and to the right behind the trachea and esophagus. This condition may be explained by the persistence of the right dorsal aorta and the obliteration of the fourth right arch. In birds, the fourth right arch forms the arch of the aorta. In reptiles, the fourth arch on both sides persists and gives rise to the double aortic arch in these animals. The heart originally lies on the ventral aspect of the pharynx, immediately behind the stomacheum. With the elongation of the neck and the development of the lungs, it recedes within the thorax, and as a consequence, the anterior ventral aortae are drawn out, and the original position of the fourth and fifth arches is greatly modified. Thus, on the right side, the fourth recedes to the root of the neck, while on the left side it is withdrawn within the thorax. The recurrent nerves originally pass to the larynx under the sixth pair of arches, and are therefore pulled backward with the descent of these structures, so that in the adult the left nerve hooks around the ligamentum arteriosum. Owing to the disappearance of the fifth and sixth right arches, the right nerve hooks around that immediately above them, i.e., the commencement of the subclavian artery. Segmental arteries arise from the primitive dorsal aortae, and course between successive segments. The seventh segmental artery is of special interest, since it forms the lower end of the vertebral artery, and, when the forelimb bud appears, sends a branch to it, the subclavian artery. From the seventh segmental arteries, the entire left subclavian and the greater part of the right subclavian are formed. The second pair of segmental arteries accompany the hypoglossal nerves to the brain, and are named the hypoglossal arteries. Each sends forward a branch which forms the cerebral part of the vertebral artery and anastomoses with the posterior branch of the internal carotid. The two vertebrals unite on the ventral surface of the hindbrain to form the basilar artery. Later, the hypoglossal artery atrophies, and the vertebral is connected with the first segmental artery. The cervical part of the vertebral is developed from a longitudinal anastomosis between the first 7 segmental arteries, so that the seventh of these ultimately becomes the source of the artery. As a result of the growth of the upper limb, the subclavian artery increases greatly in size, and the vertebral then appears to spring from it. Recent observations show that several segmental arteries contribute branches to the upper limb bud and form in it a free capillary anastomosis. Of these branches, only one, viz., that derived from the seventh segmental artery, persists to form the subclavian artery. The subclavian artery is prolonged into the limb under the names of the axillary and brachial arteries. and these together constitute the arterial stem for the upper arm. The direct continuation of this stem in the forearm is a volar interosseous artery. A branch which accompanies the median nerve soon increases in size and forms the main vessel, median artery, of the forearm, while the volar interosseous diminishes. Later, the radial and ulnar arteries are developed as branches of the brachial part of the stem, and coincidentally with their enlargement the median artery recedes. Occasionally it persists as a vessel of some considerable size, and then accompanies the median nerve into the palm of the hand. The primary arterial stem for the lower limb is formed by the inferior gluteal sciatic artery, which accompanies the sciatic nerve along the posterior aspect of the thigh to the back of the knee, whence it is continued at peroneal artery. This arrangement exists in reptiles and amphibians. The femoral artery arises later as a branch of the common iliac, and passing down the front and medial side of the thigh to the bend of the knee, joins the inferior gluteal artery. The femoral quickly enlarges, and coincidentally with this, the part of the inferior gluteal immediately above the knee undergoes atrophy. The anterior and posterior tibial arteries are branches of the main arterial stem. Further development of the veins. The formation of the great veins of the embryo may be best considered by dividing them into two groups, visceral and parietal. The visceral veins. The visceral veins are the two vitelline or omphallomesenteric veins bringing the blood from the yolk sac, and the two umbilical veins returning the blood from the placenta. These four veins open close together into the sinus venosus. The vitelline veins run upward, at first in front, and subsequently on either side of the intestinal canal. They unite on the ventral aspect of the canal, and beyond this are connected to one another by two anastomotic branches, one on the dorsal and the other on the ventral aspect of the duodenal portion of the intestine, which is thus encircled by two venous rings. Into the middle or dorsal anastomosis the superior mesenteric vein opens. The portions of the veins above the upper ring become interrupted by the developing liver and broken up by it into a plexus of small capillary-like vessels termed sinusoids, Minot. The branches conveying the blood to this plexus are named the venae advenientes, and become the branches of the portal vein, while the vessels draining the plexus into the sinus venosus are termed the venae revihentes, and form the future hepatic veins. Ultimately, the left vena reverens no longer communicates directly with the sinus venosus, but opens into the right vena reverens. The persistent part of the upper venous ring, above the opening of the superior mesenteric vein, forms the trunk of the portal vein. The two umbilical veins fuse early to form a single trunk in the body stalk, but remain separate within the embryo, and pass forward to the sinus venosus in the side walls of the body. Like the vitelline veins, their direct connection with the sinus venosus becomes interrupted by the developing liver, and thus, at this stage, the whole of the blood from the yolk sac and placenta passes through the substance of the liver before it reaches the heart. The right umbilical and right vitelline veins shrivel and disappear. The left umbilical, on the other hand, becomes enlarged, and opens into the upper venous ring of the vitelline veins. With the atrophy of the yolk sac, the left vitelline vein also undergoes atrophy and disappears. Finally, a direct branch is established between this ring and the right hepatic vein. This branch is named the ductus venosus, and enlarging rapidly, it forms a wide channel through which most of the blood, returned from the placenta, is carried direct to the heart, without passing through the liver. A small proportion of the blood from the placenta is, however, conveyed from the left umbilical vein to the liver through the left vena adveniens. The left umbilical vein and the ductus venosus undergo atrophy and obliteration after birth, and form respectively the ligamentum teres and ligamentum venosum of the liver. The parietal veins. The first indication of a parietal system consists in the appearance of two short transverse veins, the ducts of Cuvier, which open one on either side into the sinus venosus. Each of these ducts receives an ascending and descending vein. The ascending veins return the blood from the parietes of the trunk and from the Wolffian bodies, and are called cardial veins. The descending veins return the blood from the head, and are called primitive jugular veins. The blood from the lower limbs is collected by the right and left iliac and hypogastric veins, which in the earlier stages of development open into the corresponding right and left cardial veins. Later, a transverse branch, the left common iliac vein, is developed between the lower parts of the two cardial veins, and through this the blood is carried into the right cardinal vein. The portion of the left cardial vein below the left renal vein atrophies and disappears up to the point of entrance of the left spermatic vein. The portion above the left renal vein persists as a hemiazygous and accessory hemiazygous veins and the lower portion of the highest left intercostal vein. The right cardinal vein, which now receives the blood from both lower extremities, forms a large venous trunk along the posterior abdominal wall. Up to the level of the renal veins, it forms the lower part of the inferior vena cava. Above the level of the renal veins, the right cardinal vein persists as an azygous vein and receives the right intercostal veins, while the hemiazygous veins are brought into communication with it by the development of transverse branches in front of the vertebral column. Inferior vena cava. The development of the inferior vena cava is associated with the formation of two veins, the subcardinal veins. These lie parallel to and on the ventral aspect of the cardinal veins, and originate as longitudinal anastomosing channels which link up the tributaries from the mesentery to the cardinal veins. They communicate with the cardinal veins above and below, and also by a series of transverse branches. The two subcardinals are for a time connected with each other in front of the aorta by cross branches, but these disappear and are replaced by a single transverse channel at a level where the renal veins join the cardinals, and at the same level a cross-communication is established on either side between the cardinal and subcardinal. The portion of the left subcardinal behind this cross-communication disappears, while that in front, i.e. the pre-renal part, forms a connection with the ductus venosus at a point of opening of the hepatic veins, and rapidly enlarging, receives the blood from the post-renal part of the right cardinal through the cross-communication referred to. In this manner, a single trunk, the inferior vena cava, is formed, and consists of the proximal part of the ductus venosus, the pre-renal part of the right subcardinal vein, the post-renal part of the right cardinal vein, and the cross branch which joins these two veins. The left subcardinal disappears, except the part immediately in front of the renal vein, which is retained as a left suprarenal vein. The spermatic or ovarian vein opens into the post-renal of the corresponding cardinal vein. This portion of the right cardinal, as already explained, forms the lower part of the inferior vena cava, so that the right spermatic opens directly into that vessel. The post-renal segment of the left cardinal disappears, with the exception of the portion between the spermatic and renal vein, which is retained as a terminal part of the left spermatic vein. In consequence of the atrophy of the Wolffian bodies, the cardinal veins diminish in size. The primitive jugular veins, on the other hand, become enlarged, owing to the rapid development of the head and brain. They are further augmented by receiving the veins subclavian from the upper extremities, and so come to form the chief veins of the Cuvierian ducts. These ducts gradually assume an almost vertical position in consequence of the descent of the heart into the thorax. The right and left Cuvierian ducts are originally of the same diameter, and are frequently termed the right and left superior venae cavae. By the development of a transverse branch, the left innominate vein, between the two primitive jugular veins, the blood is carried across from the left to the right primitive jugular. The portion of the right primitive jugular vein between the left innominate and the azygous vein forms the upper part of the superior vena cava of the adult. The lower part of this vessel, i.e., below the entrance of the azygous vein, is formed by the right Cuvierian duct. Below the origin of the transverse branch, the left primitive jugular vein and left Cuvierian duct atrophy, the former constituting the upper part of the highest left intercostal vein, while the latter is represented by the ligament of the left vena cava, vestigial fold of Marshall, and the oblique vein of the left atrium, oblique vein of Marshall. Both right and left superior venae cavae are present in some animals, and are occasionally found in the adult human being. The oblique vein of the left atrium passes downward across the back of the left atrium to open into the coronary sinus, which, as already indicated, represents the persistent left horn of the sinus venosus. Venous sinuses of the dura mater. The primary arrangement for drainage of the capillaries of the head consists of a primary head vein, which starts in the region of the midbrain and runs caudalward along the side of the brain tube to terminate at the duct of Cuvier. The primary head vein drains three plexuses of capillaries, the anterior dural plexus, the middle dural plexus, and the posterior dural plexus. The growth of the cartilaginous capsule of the ear and the growth and alteration in form of the brain bring about changes in this primary arrangement. Owing to the growth of the otic capsule and middle ear, the course of the primary head vein becomes unfavorable, and a segment of it becomes obliterated. To make the necessary adjustment, an anastomosis is established above the otic capsule, and the middle plexus drains into the posterior plexus. Then the anterior plexus fuses with the middle plexus, and drains through it and the newly established channel dorsal to the otic capsule. All that remains of the primary head vein is a cardinal portion or internal jugular, and the part in the region of the trigeminal nerve, which may be called the cavernous sinus. Into it drain the orbital veins. The drainage from the cavernous sinus is now upward through the original trunk of the middle plexus, which is now the superior petrosal sinus, into the newly established dorsal channel. This dorsal channel is a transverse sinus. The inferior petrosal sinus appears later. From the anterior plexus a sagittal plexus extends forward, from which develops the superior sagittal sinus. The straight sinus is formed in the ventral part of the sagittal plexus. As the hemispheres extend backward, these sinuses elongate by incorporating the more caudal loops of the plexus. The anterior part of the sinus is completed first. The external jugular vein at first drains the region behind the ear, posterior auricular, and enters the primitive jugular as a lateral tributary. A group of veins from the face and lingual region converge to form a common vein, the linguofacial, which also terminates in the primitive jugular. Later, cross communication developed between the external jugular and the linguofacial, with the result that a posterior group of facial veins is transferred to the external jugular. End of section 4.
Of Gray's Anatomy, Part 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Leanne Howlett. Anatomy of the Human Body, Part 3, by Henry Gray. The Thoracic Cavity. The heart and lungs are situated in the thorax, the walls of which afford them protection. The heart lies between the two lungs, and is enclosed within a fibrous bag, the pericardium, while each lung is invested by a serous membrane, the pleura. The skeleton of the thorax and the shape and boundaries of the cavity have already been described. The cavity of the thorax. The capacity of the cavity of the thorax does not correspond with its apparent size externally, because 1. The space enclosed by the lower ribs is occupied by some of the abdominal viscera, and 2. The cavity extends above the anterior parts of the first ribs into the neck. The size of the thoracic cavity is constantly varying during life with the movements of the ribs and diaphragm, and with the degree of distension of the abdominal viscera. From the collapsed state of the lungs, as seen when the thorax is opened in the dead body, it would appear as if the viscera only partly filled the cavity, but during life there is no vacant space, that which is seen after death being filled up by the expanded lungs. The upper opening of the thorax. The parts which pass through the upper opening of the thorax are, from before backward, in or near the middle line, the sternohyoideus and sternothyroideus muscles, the remains of the thymus, the inferior thyroid veins, the trachea, esophagus, thoracic duct, and the longus colli muscles. At the sides, the innominate artery, the left common carotid, left subclavian and internal mammary arteries, and the costo-cervical trunks, the innominate veins, the vagus, cardiac, phrenic, and sympathetic nerves, the greater parts of the anterior divisions of the first thoracic nerves, and the recurrent nerve of the left side. The apex of each lung, covered by the pleura, also projects through this aperture, a little above the level of the sternal end of the first rib. The lower opening of the thorax. The lower opening of the thorax is wider transversely than from before backward. It slopes obliquely downward and backward, so that the thoracic cavity is much deeper behind than in front. The diaphragm closes the opening and forms the floor of the thorax. The floor is flatter at the center than at the sides, and higher on the right side than on the left. In the dead body the right side reaches the level of the upper border of the fifth costal cartilage, while the left extends only to the corresponding part of the sixth costal cartilage. From the highest point on each side the floor slopes suddenly downward to the costal and vertebral attachments of the diaphragm. This slope is more marked behind than in front, so that only a narrow space is left between the diaphragm and the posterior wall of the thorax. 4a. The pericardium. The pericardium is a conical fibroserous sac in which the heart and the roots of the great vessels are contained. It is placed behind the sternum and the cartilages of the third, fourth, fifth, sixth, and seventh ribs of the left side in the mediastinal cavity. In front, it is separated from the anterior wall of the thorax, in the greater part of its extent, by the lungs and pleurae, but a small area, somewhat variable in size, and usually corresponding with the left half of the lower portion of the body of the sternum and the medial ends of the cartilages of the fourth and fifth ribs of the left side, comes into direct relationship with the chest wall. The lower extremity of the thymus, in the child, is in contact with the front of the upper part of the pericardium. Behind, it rests upon the bronchi, the esophagus, the descending thoracic aorta, and the posterior part of the mediastinal surface of each lung. Laterally it is covered by the pleurae, and is in relation with the mediastinal surfaces of the lungs. The phrenic nerve, with its accompanying vessels, descends between the pericardium and pleura on either side. Structure of the pericardium. Although the pericardium is usually described as a single sac, an examination of its structure shows that it consists essentially of two sacs intimately connected with one another, but totally different in structure. The outer sac, known as the fibrous pericardium, consists of fibrous tissue. The inner sac, or serous pericardium, is a delicate membrane which lies within the fibrous sac and lines its walls. It is composed of a single layer of flattened cells resting on loose connective tissue. The heart invaginates the wall of the serous sac from above and behind, and practically obliterates its cavity, the space being merely a potential one. The fibrous pericardium forms a flask-shaped bag, the neck of which is closed by its fusion with the external coats of the great vessels, while its base is attached to the central tendon and to the muscular fibers of the left side of the diaphragm. In some of the lower mammals the base is either completely separated from the diaphragm or joined to it by some loose areolar tissue. In man, much of its diaphragmatic attachment consists of loose fibrous tissue which can be readily broken down, but over a small area the central tendon of the diaphragm and the pericardium are completely fused. Above, the fibrous pericardium not only blends with the external coats of the great vessels, but is continuous with the pretracheal layer of the deep cervical fascia. By means of these upper and lower connections it is securely anchored within the thoracic cavity. It is also attached to the posterior surface of the sternum by the superior and inferior sterno-pericardiac ligaments, the upper passing to the manubrium, and the lower to the xiphoid process. The vessels receiving fibrous prolongations from this membrane are the aorta, the superior vena cava, the right and left pulmonary arteries, and the four pulmonary veins. The inferior vena cava enters the pericardium through the central tendon of the diaphragm and receives no covering from the fibrous layer. The serous pericardium is, as already stated, a closed sac which lines the fibrous pericardium and is invaginated by the heart. It therefore consists of a visceral and a parietal portion. The visceral portion, or epicardium, covers the heart and the great vessels, and from the latter is continuous with the parietal layer which lines the fibrous pericardium. The portion which covers the vessels is arranged in the form of two tubes. The aorta and pulmonary artery are enclosed in one tube, the arterial mesocardium. The superior and inferior venae cavae and the four pulmonary veins are enclosed in a second tube, the venous mesocardium, the attachment of which to the parietal layer presents the shape of an inverted U. The cul-de-sac enclosed between the limbs of the U lies behind the left atrium and is known as the oblique sinus, while the passage between the venous and arterial mesocardia, that is, between the aorta and pulmonary artery in front and the atria behind, is termed the transverse sinus. The ligament of the left vena cava. Between the left pulmonary artery and subjacent pulmonary vein is a triangular fold of the serous pericardium. It is known as the ligament of the left vena cava, vestigial fold of Marshall. It is formed by the duplicature of the serous layer over the remnant of the lower part of the left superior vena cava, duct of Cuvier, which becomes obliterated during fetal life and remains as a fibrous band stretching from the highest left intercostal vein to the left atrium, where it is continuous with a small vein, the vein of the left atrium, oblique vein of Marshall, which opens into the coronary sinus. The arteries of the pericardium are derived from the internal mammary and its musculophrenic branch, and from the descending thoracic aorta. The nerves of the pericardium are derived from the vagus and phrenic nerves and the sympathetic trunks. End of section 5. Recording by Leanne Howlett.
Of Gray's Anatomy, Part 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Laurie Ann Walden. Anatomy of the Human Body, Part 3, by Henry Gray. The Heart, Core. The heart is a hollow muscular organ of a somewhat conical form. It lies between the lungs and the middle mediastinum, and is enclosed in the pericardium. It is placed obliquely in the chest behind the body of the sternum and adjoining parts of the rib cartilages, and projects farther into the left than into the right half of the thoracic cavity, so that about 1/3 of it is situated on the right and 2/3 on the left of the median plane. Size. The heart in the adult measures about 12 cm in length, 8 to 9 cm in breadth at the broadest point, and 6 cm in thickness. Its weight in the male varies from 280 to 340 grams, in the female from 230 to 280 grams. The heart continues to increase in weight and size up to an advanced period of life. This increase is more marked in men than in women. Component parts. As has already been stated, the heart is subdivided by septa into right and left halves, and a constriction subdivides each half of the organ into two cavities, the upper cavity being called the atrium, the lower the ventricle. The heart, therefore, consists of 4 chambers, that is, right and left atria, and right and left ventricles. The division of the heart into 4 cavities is indicated on its surface by grooves. The atria are separated from the ventricles by the coronary sulcus, auriculoventricular groove. This contains the trunks of the nutrient vessels of the heart, and is deficient in front, where it is crossed by the root of the pulmonary artery. The interatrial groove, separating the 2 atria, is scarcely marked on the posterior surface, while anteriorly it is hidden by the pulmonary artery and aorta. The ventricles are separated by 2 grooves, one of which, the anterior longitudinal sulcus, is situated on the sternocostal surface of the heart, close to its left margin. The other, posterior longitudinal sulcus, on the diaphragmatic surface near the right margin. These grooves extend from the base of the ventricular portion to a notch, the incisura apicis cordis, on the acute margin of the heart, just to the right of the apex. The base, basis cordis, directed upward, backward, and to the right, is separated from the 5th, 6th, 7th, and 8th thoracic vertebrae by the esophagus, aorta, and thoracic duct. It is formed mainly by the left atrium, and, to a small extent, by the back part of the right atrium. Somewhat quadrilateral in form, it is in relation above with the bifurcation of the pulmonary artery, and is bounded below by the posterior part of the coronary sulcus, containing the coronary sinus. On the right it is limited by the sulcus terminalis of the right atrium, and on the left by the ligament of the left vena cava and the oblique vein of the left atrium. The 4 pulmonary veins, 2 on either side, open into the left atrium, while the superior vena cava opens into the upper, and the anterior vena cava into the lower, part of the right atrium. The apex, apex cordis. The apex is directed downward, forward, and to the left, and is overlapped by the left lung and pleura. It lies behind the 5th left intercostal space, 8 to 9 centimeters from the midsternal line, or about 4 centimeters below and 2 millimeters to the medial side of the left mammary papilla. The sternocostal surface is directed forward, upward, and to the left. Its lower part is convex, formed chiefly by the right ventricle, and traversed near its left margin by the anterior longitudinal sulcus. Its upper part is separated from the lower by the coronary sulcus, and is formed by the atria. It presents a deep concavity, occupied by the ascending aorta and the pulmonary artery. The diaphragmatic surface, directed downward and slightly backward, is formed by the ventricles, and rests upon the central tendon and a small part of the left muscular portion of the diaphragm. It is separated from the base by the posterior part of the coronary sulcus, and is traversed obliquely by the posterior longitudinal sulcus. The right margin of the heart is long, and is formed by the right atrium above and the right ventricle below. The atrial portion is rounded and almost vertical, It is situated behind the third, fourth, and fifth right costal cartilages, about 1.25 centimeters from the margin of the sternum. The ventricular portion, thin and sharp, is named the acute margin. It is nearly horizontal and extends from the sternal end of the sixth right costal cartilage to the apex of the heart. The left or obtuse margin is shorter, full, and rounded. It is formed mainly by the left ventricle, but to a slight extent above by the left atrium. It extends from a point in the second left intercostal space, about 2.5 millimeters from the sternal margin, obliquely downward, with a convexity to the left, to the apex of the heart. Right atrium, atrium dextrum, right auricle. The right atrium is larger than the left, but its walls are somewhat thinner, measuring about 2 millimeters. Its cavity is capable of containing about 57 cc. It consists of two parts, a principal cavity, or sinus venerum, situated posteriorly, and an anterior, smaller portion, the auricula. Sinus venerum, sinus venosus. The sinus venarum is the large quadrangular cavity placed between the two vena cavae. Its walls, which are extremely thin, are connected below with the right ventricle, and medially with the left atrium, but are free in the rest of their extent. Auricula, auricula dextra, right auricular appendix. The auricula is a small conical muscular pouch, the margins of which present a dentated edge. It projects from the upper and front part of the sinus forward and toward the left side, overlapping the root of the aorta. The separation of the auricula from the sinus venarum is indicated externally by a groove, the terminal sulcus, which extends from the front of the superior vena cava to the front of the inferior vena cava, and represents the line of union of the sinus venosus of the embryo with the primitive atrium. On the inner wall of the atrium the separation is marked by a vertical, smooth muscular ridge, the terminal crest. Behind the crest the internal surface of the atrium is smooth, while in front of it the muscular fibers of the wall are raised into parallel ridges resembling the teeth of a comb, and hence named the musculi pectinati. Its interior presents the following parts for examination: openings: superior vena cava, inferior vena cava, coronary sinus, foramina venarum minimarum, atrioventricular. Valves: valve of the inferior vena cava, valve of the coronary sinus, fossa ovalis, limbus fossae ovalis, intervenous tubercle, musculi pectinati, crista terminalis. The superior vena cava returns the blood from the upper half of the body, and opens into the upper and back part of the atrium, the direction of its orifice being downward and forward. Its opening has no valve. The inferior vena cava, larger than the superior, returns the blood from the lower half of the body, and opens into the lowest part of the atrium near the atrial septum, its orifice being directed upward and backward, and guarded by a rudimentary valve, the valve of the inferior vena cava, Eustachian valve. The blood entering the atrium through the superior vena cava is directed downward and forward, that is, toward the atrioventricular orifice, while that entering through the inferior vena cava is directed upward and backward, toward the atrial septum. This is the normal direction of the two currents in fetal life. The coronary sinus opens into the atrium between the orifice of the inferior vena cava and the atrioventricular opening. It returns blood from the substance of the heart, and is protected by a semicircular valve, the valve of the coronary sinus, valve of Thebesius. The foramina venarum minimarum, foramina Thebesii, are the orifices of minute veins, veni cordis minimi, which return blood directly from the muscular substance of the heart. The atrioventricular opening, tricuspid orifice, is the large oval aperture of communication between the atrium and the ventricle. It will be described with the right ventricle. The valve of the inferior vena cava, valvula vena cavae inferioris or Eustachii, Eustachian valve, is situated in front of the orifice of the inferior vena cava. It is semilunar in form, its convex margin being attached to the anterior margin of the orifice. Its concave margin, which is free, ends in two cornua, of which the left is continuous with the anterior edge of the limbus fossae ovalis, while the right is lost on the wall of the atrium. The valve is formed by a duplicature of the lining membrane of the atrium, containing a few muscular fibers. In the fetus this valve is of large size, and serves to direct the blood from the inferior vena cava through the foramen ovale into the left atrium. In the adult it occasionally persists, and may assist in preventing the reflux of blood into the inferior vena cava. More commonly it is small, and may present a cribriform or filamentous appearance. Sometimes it is altogether wanting. The valve of the coronary sinus, valvula sinus coronarii, or Thebesii, Thebesian valve, is a semicircular fold of the lining membrane of the atrium, at the orifice of the coronary sinus. It prevents the regurgitation of blood into the sinus during the contraction of the atrium. This valve may be double, or it may be cribriform. The fossa ovalis is an oval depression on the septal wall of the atrium, and corresponds to the situation of the foramen ovale in the fetus. It is situated at the lower part of the septum, above and to the left of the orifice of the inferior vena cava. The limbus fossae ovalis, annulus ovalis, is the prominent oval margin of the fossa ovalis. It is most distinct above and at the sides of the fossa. Below it is deficient. A small slit-like valvular opening is occasionally found at the upper margin of the fossa, leading upward beneath the limbus into the left atrium. It is the remains of the fetal aperture between the two atria. The intervenous tubercle, tuberculum intervenosum, tubercle of Lower, is a small projection on the posterior wall of the atrium above the fossa ovalis. It is distinct in the hearts of quadrupeds, but in man is scarcely visible. It was supposed by Lower to direct the blood from the superior vena cava toward the atrioventricular opening. Right ventricle, ventriculus dexter. The right ventricle is triangular in form, and extends from the right atrium to near the apex of the heart. Its antero-superior surface is rounded and convex, and forms the larger part of the sternocostal surface of the heart. Its under surface is flattened, rests upon the diaphragm, and forms a small part of the diaphragmatic surface of the heart. Its posterior wall is formed by the ventricular septum, which bulges into the right ventricle, so that a transverse section of the cavity presents a semilunar outline. Its upper and left angle forms a conical pouch, the conus arteriosus, from which the pulmonary artery arises. A tendinous band, which may be named the tendon of the conus arteriosus, extends upward from the right atrioventricular fibrous ring, and connects the posterior surface of the conus arteriosus to the aorta. The wall of the right ventricle is thinner than that of the left, the proportion between them being as 1:3. It is thickest at the base, and gradually becomes thinner toward the apex. The cavity equals in size that of the left ventricle, and is capable of containing about 85 cc. Its interior presents the following parts for examination: openings, right atrioventricular, pulmonary artery; valves, tricuspid, pulmonary; trabeculi carni, chordi tendini. The right atrioventricular orifice is the large oval aperture of communication between the right atrium and ventricle. Situated at the base of the ventricle, it measures about 4 cm in diameter, and is surrounded by a fibrous ring, covered by the lining membrane of the heart. It is considerably larger than the corresponding aperture on the left side, being sufficient to admit the ends of 4 fingers. It is guarded by the tricuspid valve. The opening of the pulmonary artery is circular in form, and situated at the summit of the conus arteriosus, close to the ventricular septum. It is placed above and to the left of the atrioventricular opening, and is guarded by the pulmonary semilunar valves. The tricuspid valve, valvula tricuspidalis, consists of 3 somewhat triangular cusps, or segments. The largest cusp is interposed between the atrioventricular orifice and the conus arteriosus, and is termed the anterior or infundibular cusp. A second, the posterior or marginal cusp, is in relation to the right margin of the ventricle, and a third, the medial or septal cusp, to the ventricular septum. They are formed by duplicatures of the lining membrane of the heart, strengthened by intervening layers of fibrous tissue. Their central parts are thick and strong, their marginal portions thin and translucent, and in the angles between the latter small intermediate segments are sometimes seen. Their bases are attached to a fibrous ring surrounding the atrioventricular orifice, and are also joined to each other so as to form a continuous annular membrane, while their apices project into the ventricular cavity. Their atrial surfaces, directed toward the blood current from the atrium, are smooth; their ventricular surfaces, directed toward the wall of the ventricle, are rough and irregular, and together with the apices and margins of the cusps, give attachment to a number of delicate tendinous cords, the chordae tendineae. The trabeculae carni, columnae carni, are rounded or irregular muscular columns which project from the whole of the inner surface of the ventricle, with the exception of the conus arteriosus. They are of three kinds. Some are attached along their entire length on one side, and merely form prominent ridges. Others are fixed at their extremities, but free in the middle; while a third set, musculi papillares, are continuous by their bases with the wall of the ventricle, while their apices give origin to the chordae tendineae which pass to be attached to the segments of the tricuspid valve. There are two papillary muscles, anterior and posterior. Of these the anterior is the larger, and its chordae tendineae are connected with the anterior and posterior cusps of the valve. The posterior papillary muscle sometimes consists of 2 or 3 parts; its chordae tendineae are connected with the posterior and medial cusps. In addition to these, some chordae tendineae spring directly from the ventricular septum or from small papillary eminences on it, and pass to the anterior and medial cusps. A muscular band, well marked in sheep and some other animals, frequently extends from the base of the anterior papillary muscle to the ventricular septum. From its attachments it may assist in preventing over-distension of the ventricle, and so has been named the moderator band. The pulmonary semilunar valves are 3 in number, 2 in front and 1 behind, formed by duplicatures of the lining membrane, strengthened by fibrous tissue. They are attached by their convex margins to the wall of the artery at its junction with the ventricle, their free borders being directed upward into the lumen of the vessel. The free and attached margins of each are strengthened by tendinous fibers, and the former presents, at its middle, a thickened nodule, corpus aurantii. From this nodule tendinous fibers radiate through the segment to its attached margin, but are absent from 2 narrow crescentic portions, the lunulae, placed one on either side of the nodule immediately adjoining the free margin. Between the semilunar valves and the wall of the pulmonary artery are 3 pouches or sinuses, sinuses of Valsalva. Left atrium, atrium sinistrum, left auricle. The left atrium is rather smaller than the right, but its walls are thicker, measuring about 3 millimeters. It consists, like the right, of 2 parts, a principal cavity and an auricula. The principal cavity is cuboidal in form, and concealed in front by the pulmonary artery and aorta. In front and to the right it is separated from the right atrium by the atrial septum. Opening into it on either side are the 2 pulmonary veins. Auricula, auricula sinistra, left auricular appendix. The auricula is somewhat constricted at its junction with the principal cavity. It is longer, narrower, and more curved than that of the right side. Its margins are more deeply indented. It is directed forward and toward the right, and overlaps the root of the pulmonary artery. The interior of the left atrium presents the following parts for examination: openings of the 4 pulmonary veins, left atrioventricular opening, musculi pectinati. The pulmonary veins, 4 in number, open into the upper part of the posterior surface of the left atrium, 2 on either side of its middle line. They are not provided with valves. The 2 left veins frequently end by a common opening. The left atrioventricular opening is the aperture between the left atrium and ventricle, and is rather smaller than the corresponding opening on the right side. The musculi pectinati, fewer and smaller than in the right auricula, are confined to the inner surface of the auricula. On the atrial septum may be seen a lunated impression, bounded below by a crescentic ridge, the concavity of which is turned upward. The depression is just above the fossa ovalis of the right atrium. End of section 6. Of Gray's Anatomy Part 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Laurie Ann Walden. Anatomy of the Human Body, Part 3, by Henry Gray. The Heart, Part 2. Left ventricle, ventriculus sinister. The left ventricle is longer and more conical in shape than the right, and on transverse section its concavity presents an oval or nearly circular outline. It forms a small part of the sternocostal surface and a considerable part of the diaphragmatic surface of the heart. It also forms the apex of the heart. Its walls are about 3 times as thick as those of the right ventricle. Its interior presents the following parts for examination. Openings: left atrioventricular, aortic. Valves: bicuspid or mitral, aortic. Trabeculae carni, chordae tendineae. The left atrioventricular opening, mitral orifice, is placed below and to the left of the aortic orifice. It is a little smaller than the corresponding aperture of the opposite side, admitting only 2 fingers. It is surrounded by a dense fibrous ring covered by the lining membrane of the heart, and is guarded by the bicuspid or mitral valve. The aortic opening is a circular aperture in front and to the right of the atrioventricular, from which it is separated by the anterior cusp of the bicuspid valve. Its orifice is guarded by the aortic semilunar valves. The portion of the ventricle immediately below the aortic orifice is termed the aortic vestibule, and possesses fibrous instead of muscular walls. The bicuspid or mitral valve, valvula bicuspidalis or mitralis, is attached to the circumference of the left atrioventricular orifice in the same way that the tricuspid valve is on the opposite side. It consists of 2 triangular cusps formed by duplicatures of the lining membrane, strengthened by fibrous tissue, and containing a few muscular fibers. The cusps are of unequal size, and are larger, thicker, and stronger than those of the tricuspid valve. The larger cusp is placed in front and to the right between the atrioventricular and aortic orifices, and is known as the anterior or aortic cusp. The smaller or posterior cusp is placed behind and to the left of the opening. 2 smaller cusps are usually found at the angles of junction of the larger. The cusps of the bicuspid valve are furnished with chordae tendineae, which are attached in a manner similar to those on the right side. They are, however, thicker, stronger, and less numerous. The aortic semilunar valves are 3 in number, and surround the orifice of the aorta. 2 are anterior, right and left, and 1 posterior. They are similar in structure and in their mode of attachment to the pulmonary semilunar valves, but are larger, thicker, and stronger. The lunulae are more distinct, and the noduli or corpora arantii thicker and more prominent. Opposite the valves, the aorta presents slight dilatations, the aortic sinuses of Valsalva, which are larger than those at the origin of the pulmonary artery. The trabeculae carneae are of 3 kinds, like those upon the right side, but they are more numerous, and present a dense interlacement, especially at the apex and upon the posterior wall of the ventricle. The musculi papillaris are 2 in number, one being connected to the anterior, the other to the posterior wall. They are of large size, and end in rounded extremities, from which the chordae tendineae arise. The chordae tendineae from each papillary muscle are connected to both cusps of the bicuspid valve. Ventricular septum, septum ventriculorum, interventricular septum. The ventricular septum is directed obliquely backward and to the right, and is curved, with a convexity toward the right ventricle. Its margins correspond with the anterior and posterior longitudinal sulci. The greater portion of it is thick and muscular, and constitutes the muscular ventricular septum; but its upper and posterior part, which separates the aortic vestibule from the lower part of the right atrium and upper part of the right ventricle, is thin and fibrous, and is termed the membranous ventricular septum. An abnormal communication may exist between the ventricles at this part, owing to defective development of the membranous septum. Structure. The heart consists of muscular fibers and of fibrous rings which serve for their attachment. It is covered by the visceral layer of the serous pericardium (epicardium) and lined by the endocardium. Between these two membranes is the muscular wall, or myocardium. The endocardium is a thin, smooth membrane which lines and gives the glistening appearance to the inner surface of the heart. It assists in forming the valves by its reduplications, and is continuous with the lining membrane of the large blood vessels. It consists of connective tissue and elastic fibers, and is attached to the muscular structure by loose elastic tissue, which contains blood vessels and nerves. Its free surface is covered by endothelial cells. The fibrous rings surround the atrioventricular and arterial orifices, and are stronger upon the left than on the right side of the heart. The atrioventricular rings serve for the attachment of the muscular fibers of the atria and ventricles, and for the attachment of the bicuspid and tricuspid valves. The left atrioventricular ring is closely connected, by its right margin, with the aortic arterial ring. Between these and the right atrioventricular ring is a triangular mass of fibrous tissue, the trigonum fibrosum, which represents the os cordis seen in the heart of some of the larger animals, as the ox and elephant. Lastly, there is the tendinous band, already referred to, the posterior surface of the conus arteriosus. The fibrous rings surrounding the arterial orifices serve for the attachment of the great vessels and semilunar valves. Each ring receives, by its ventricular margin, the attachment of some of the muscular fibers of the ventricles. Its opposite margin presents 3 deep semicircular notches to which the middle coat of the artery is firmly fixed. The attachment of the artery to its fibrous ring is strengthened by the external coat and serous membrane externally, and by the endocardium internally. From the margins of the semicircular notches, the fibrous structure of the ring is continued into the segments of the valves. The middle coat of the artery in this situation is thin, and the vessel is dilated to form the sinuses of the aorta and pulmonary artery. Cardiac muscular tissue. The fibers of the heart differ very remarkably from those of other striped muscles. They are smaller by 1/3, and their transverse striae are by no means so well marked. They show faint longitudinal striation. The fibers are made up of distinct quadrangular cells, joined end to end so as to form a syncytium. Each cell contains a clear oval nucleus situated near its center. The extremities of the cells have a tendency to branch or divide, the subdivisions uniting with offsets from other cells, and thus producing an anastomosis of the fibers. The connective tissue between the bundles of fibers is much less than in ordinary striped muscle, and no sarcolemma has been proved to exist. Purkinje fibers. Between the endocardium and the ordinary cardiac muscle are found, embedded in a small amount of connective tissue, peculiar fibers known as Purkinje fibers. They are found in certain mammals and in birds, and can be best seen in the sheep's heart, where they form a considerable portion of the moderator band, and also appear as gelatinous-looking strands on the inner walls of the atria and ventricles. They also occur in the human heart, associated with the terminal distributions of the bundle of His. The fibers are very much larger in size than the cardiac cells, and differ from them in several ways. In longitudinal section they are quadrilateral in shape, being about twice as long as they are broad. The central portion of each fiber contains one or more nuclei, and is made up of granular protoplasm, with no indication of striations, while the peripheral portion is clear and has distinct transverse striations. The fibers are intimately connected with each other, possess no definite sarcolemma, and do not branch. The muscular structure of the heart consists of bands of fibers which present an exceedingly intricate interlacement. They comprise a. the fibers of the atria, b. the fibers of the ventricles, and c. the atrioventricular bundle of His. The fibers of the atria are arranged in two layers, a superficial, common to both cavities, and a deep, proper to each. The superficial fibers are most distinct on the front of the atria, across the bases of which they run in a transverse direction, forming a thin and incomplete layer. Some of these fibers run into the atrial septum. The deep fibers consist of looped and annular fibers. The looped fibers pass upward over each atrium, being attached by their two extremities to the corresponding atrioventricular ring, in front and behind. The annular fibers surround the auriculae, and form annular bands around the terminations of the veins and around the fossa ovalis. The fibers of the ventricles are arranged in a complex manner, and various accounts have been given of their course and connections. The following description is based on the work of McCallum. They consist of superficial and deep layers, all of which, with the exception of two, are inserted into the papillary muscles of the ventricles. The superficial layers consist of the following: a. Fibers which spring from the tendon of the conus arteriosus and sweep downward and toward the left across the anterior longitudinal sulcus and around the apex of the heart, where they pass upward and inward to terminate in the papillary muscles of the left ventricle. Those arising from the upper half of the tendon of the conus arteriosus pass to the anterior papillary muscle. Those from the lower half to the posterior papillary muscle and the papillary muscles of the septum. b. Fibers which arise from the right atrioventricular ring and run diagonally across the diaphragmatic surface of the right ventricle and around its right border onto its costosternal surface, where they dip beneath the fibers just described, and, crossing the anterior longitudinal sulcus, wind around the apex of the heart and end in the posterior papillary muscle of the left ventricle. c. Fibers which spring from the left atrioventricular ring and, crossing the posterior longitudinal sulcus, pass successively into the right ventricle and end in its papillary muscles. The deep layers are 3 in number. They arise in the papillary muscles of one ventricle and, curving in an S-shaped manner, turn in at the longitudinal sulcus and end in the papillary muscles of the other ventricle. The layer which is most superficial in the right ventricle lies next the lumen of the left, and vice versa. Those of the first layer almost encircle the right ventricle, and, crossing in the septum to the left, unite with the superficial fibers from the right atrioventricular ring to form the posterior papillary muscle. Those of the second layer have a less extensive course in the wall of the right ventricle, and a correspondingly greater course in the left, where they join with the superficial fibers from the anterior half of the tendon of the conus arteriosus to form the papillary muscles of the septum. Those of the third layer pass almost entirely around the left ventricle and unite with the superficial fibers from the lower half of the tendon of the conus arteriosus to form the anterior papillary muscle. Besides the layers just described, there are 2 bands which do not end in papillary muscles. One springs from the right atrioventricular ring and crosses in the atrioventricular septum. It then encircles the deep layers of the left ventricle and ends in the left atrioventricular ring. The second band is apparently confined to the left ventricle. It is attached to the left atrioventricular ring, and encircles the portion of the ventricle adjacent to the aortic orifice. The atrioventricular bundle of His is the only direct muscular connection known to exist between the atria and the ventricles. Its cells differ from ordinary cardiac muscle cells in being more spindle-shaped. They are, moreover, more loosely arranged and have a richer vascular supply than the rest of the heart muscle. It arises in connection with 2 small collections of spindle-shaped cells, the sinoatrial and atrioventricular nodes. The sinoatrial node is situated on the anterior border of the opening of the superior vena cava. From it strands of fusiform fibers run under the endocardium of the wall of the atrium to the atrioventricular node. The atrioventricular node lies near the orifice of the coronary sinus in the annular and septal fibers of the right atrium. From it the atrioventricular bundle passes forward in the lower part of the membranous septum and divides into right and left fasciculi. These run down in the right and left ventricles, one on either side of the ventricular septum, covered by endocardium. In the lower parts of the ventricles they break up into numerous strands which end in the papillary muscles, and in the ventricular muscle generally. The greater portion of the atrioventricular bundle consists of narrow, somewhat fusiform fibers, but its terminal strands are composed of Purkinje fibers. Dr. A. Morrison has shown that in the sheep and pig the atrioventricular bundle is a great avenue for the transmission of nerves from the auricular to the ventricular heart, large and numerous nerve trunks entering the bundle and coursing with it. From these, branches pass off and form plexuses around groups of Purkinje cells, and from these plexuses fine fibrils go to innervate individual cells. Clinical and experimental evidence go to prove that this bundle conveys the impulse to systolic contraction from the atrial septum to the ventricles. Vessels and nerves. The arteries supplying the heart are the right and left coronary from the aorta. The veins end in the right atrium. The lymphatics end in the thoracic and right lymphatic ducts. The nerves are derived from the cardiac plexus, which are formed partly from the vagi and partly from the sympathetic trunks. They are freely distributed both on the surface and in the substance of the heart, the separate nerve filaments being furnished with small ganglia. The cardiac cycle and the actions of the valves. By the contractions of the heart, the blood is pumped through the arteries to all parts of the body. These contractions occur regularly, and at the rate of about 70 per minute. Each wave of contraction, or period of activity, is followed by a period of rest, the two periods constituting what is known as a cardiac cycle. Each cardiac cycle consists of 3 phases, which succeed each other as follows. 1. A short simultaneous contraction of both atria, termed the atrial systole, followed, after a slight pause, by 2. A simultaneous, but more prolonged, contraction of both ventricles, named the ventricular systole, and 3. A period of rest, during which the whole heart is relaxed. The atrial contraction commences around the venous openings, and sweeping over the atria forces their contents through the atrioventricular openings into the ventricles, regurgitation into the veins being prevented by the contraction of their muscular coats. When the ventricles contract, the tricuspid and bicuspid valves are closed and prevent the passage of the blood back into the atria. The musculi papillaris at the same time are shortened, and pulling on the chordae tendineae prevent the inversion of the valves into the atria. As soon as the pressure in the ventricles exceeds that in the pulmonary artery and aorta, the valves guarding the orifices of these vessels are opened, and the blood is driven from the right ventricle into the pulmonary artery, and from the left into the aorta. The moment the systole of the ventricles ceases, the pressure of the blood in the pulmonary artery and aorta closes the pulmonary and aortic semilunar valves to prevent regurgitation of blood into the ventricles, the valves remaining shut until reopened by the next ventricular systole. During the period of rest, the tension of the tricuspid and bicuspid valves is relaxed, and blood is flowing from the veins into the atria, being aspirated by negative intrathoracic pressure, and slightly also from the atria into the ventricles. The average duration of a cardiac cycle is about 0.8 of a second, made up as follows: atrial systole 1/10, atrial diastole 7/10, ventricular systole 3/10, ventricular diastole 5/10, total systole 4/10, complete diastole 4/10. The rhythmical action of the heart is muscular in origin. That is to say, the heart muscle itself possesses the inherent property of contraction, apart from any nervous stimulation. The more embryonic the muscle, the better is it able to initiate and propagate the contraction wave. This explains why the normal systole of the heart starts at the entrance of the veins, for there the muscle is most embryonic in nature. At the atrioventricular junction there is a slight pause in the wave of muscular contraction. To obviate this so far as possible, a peculiar band of marked embryonic type passes across the junction, and so carries on the contraction wave to the ventricles. This band, composed of special fibers, is the atrioventricular bundle of His. The nerves, although not concerned in originating the contractions of the heart muscle, play an important role in regulating their force and frequency in order to subserve the physiological needs of the organism. End of section 7.